This problem presents a geared system in which we have a shaft under torque that is going to be twisting. And to solve this problem, we're going to follow the process described by Crandall Don Lardner of using three categories. The first category being equilibrium, the second being geometric compatibility, and the third being constitutive relationships. And the goal is to figure out what the angle of twist in shaft AB might be in degrees. So we'll have to convert at the end. To get started, let's go ahead and draw the shaft in question. So here we have shaft AB, as you see, and we'll go ahead and apply external torques as we suspect they might be applied. We can see that there's a hanging mass here that is applying a torque to the A end of the shaft in this direction, as you see here. We don't have to follow a convention when we use or when we apply external torques or loads to a system. And TB will go ahead and say it's probably doing the opposite. This system is in equilibrium and it's precariously balancing a shaft or a mass M2 and a mass M1. Let's go ahead and take a look at what's happening inside this shaft. If we draw just a portion from A to B, as you see here, we'll have that torque TA, which is the same one that we drew there. We'll have a torque internal TAB, as you see here, and we'll be able to see that TAB is equal to TA. Now, where does this TA look or apply its load as we look at this entire system? Well, it's applying it right here. And how is that torque being applied? It's being applied by a lever arm right there, and we can draw that, and it has length A2, and it's going to have M2G hanging down from this side, and so the torque that has to resist that, the equal and opposite torque, right? We have the TA going this direction at point A, and then this TA acting in this direction on this lever arm that we have suspended there, and we see that in equilibrium we'll have the following, that this TA torque is going to be equal to M2G, that's weight, times the lever arm's length. Now what do we do next? Well, let's take a look at what happens in terms of geometric compatibility. Here is shaft AB again, and this time we might consider a convention that we would use if we had sliced the ends of the shaft. Okay, so imagine that we're internally, we drew a little squiggly here or a little squiggly here, and we're just inside. So the convention that we would use to describe angular displacement would be for the face coming out to have a vector and the angular displacement defined as positive when it's in alignment with that normal vector. We can do the same for the other side, and we say we have a phi BA on the opposite side. Now, I understand that these conventions can be a little bit idiosyncratic and can be a little bit different depending on how you're thinking about a problem. So these conventions, or this way of setting up the angular displacements, is not set in stone. But if we do it this way, what we see is that we can describe, and this is just for deformation, right? If we think of how is A, if we were to keep B fixed here, how is A going to displace angularly with respect to B? Okay, that's what A/B is going to mean in the context of what we're doing here. And conversely, how is B, if we keep A fixed, going to have its angular displacement or displace angularly at this end with respect to A? Okay, and so we see that using this convention, we have that phi A/B, or phi A relative to B, is equal to phi B relative to A. Now, this is not necessarily rocket science or earth-shattering, but it helps us be able to get an idea of what the angle of twist that we're interested in having here might be. So this angle of twist, if we look at it And this is maybe another insight we'll say is that this question is not saying, okay, uh, phi A relative to B. It's just saying what is the angle of twist of shaft AB in degrees. So if we're looking at the problem from the perspective of I just want a quantitative scalar that gives me a magnitude, I can take the magnitude of this, because if we look at it, the way we've kind of got things defined here, we might be getting confused between, okay, is it positive or negative? So let's not focus too much on that. We're just going to focus on the magnitude of this angular displacement or angular twist, angle of twist. So the angle of twist, going up now to our constitutive relationships, is going to be given by our TL over JG. What is the T? The T is going to be this TA torque, right? What is the L? Well, the L is the length of this shaft, okay? J and G, we'll come back to them in a second, but we can rewrite this as M2GA2, so we take the TA from down here, put it up here, and then the L2 is the length of the shaft. And now we have it over JG. So in the pursuit of trying to figure out what J and G are, we can go ahead and take a further look at the problem. It says that shaft AB has a diameter of 1 centimeter. So that means that C2, if we want to call it, or the radius of this shaft, would be half of that, which would be half a centimeter. And we can write out that the second moment of inertia is going to be pi over 2 C2 to the fourth. Okay, so that solves that part of the problem, that J2 will be given by half, or this pi over 2 C2 to the fourth, where C2 is equal to 0.5 centimeters. The G is the shear modulus, and this problem did not explicitly give us the shear modulus, so we have to calculate that out based on what we're given with an elastic modulus and a Poisson's ratio. And so this is the relationship that we've described and will allow us to be able to calculate the shear modulus. So in the end, the phi A relative to B is going to be equal to this numerator over the J2G, and we substitute in appropriately. Let's go ahead and use Colab or IPython to solve this problem. We'll bring up, let's see here. Yes, oh no, I just deleted my blast. I just deleted that. So, well, let's go back into Drive, and we'll go into, hopefully this is not too much. Here we go. All right. And we'll go ahead and, sorry, you have to bear this. And here we go. All right. So let's go ahead and we will create a new collab, just like this. And we'll go ahead and make this a little bit smaller so we can attempt to see what the parameters are as we're solving things. We'll import numpy. And whoa, I'm not going to create a new cell. I'll just leave it like that because this shouldn't be too lengthy of a problem. M2 is going to be 10 kilograms. G, we said it was 9.8 meters per second squared. A2 is equal to 4 centimeters, so we'll do 4e to minus 10 to the minus 2. That will give us units of meters. We need an L2, and L2 was given as 11 centimeters, so we'll do that as 11e minus 2. We need a G and a J2, so let's go ahead and, well, for J, we need a C2, which is going to be 0.5. That'll keep us in meters. The G is going to need an elastic modulus, so that's 207 E9. And That will give us the units in pascals, and the Poisson ratio nu is 0.31. Okay, so let's go ahead and solve J2, and that's going to be mp dot pi divided by 2 times c 2 to the fourth. Okay, and that will end up having units of meters to the fourth. We have a g, which will end up having units of pascals. It's just E divided by quantity 2 times 1 plus nu, as we see here. This we can say it's units of pascals. So now we can say that phi A, B is going to be equal to m2 times g times a2 times L2 divided by quantity j2 times g. Okay. And we'll go ahead and print this up, saying that we're trying to describe our phi A relative to B. And we'll, MP round. And okay, this will give it to us in radians if we don't do anything. If we want to convert to degrees, okay, so I guess I can say this is in radians. If I want to convert to degrees, right, I need to multiply by 180 over pi, like that. And then I'm going to say that this will be in units of degrees. Okay. I didn't say how much to round. Let's say we're going to round, I don't know, to 3 decimal places. That might be a little excessive, and let's see what we get. So it's going ahead and it's starting to run things, and it's initializing things, and then it runs. And what do we get? Well, we get 0.319 degrees. And that is not a tremendous amount, right, of angle of twist that we have. And, you know, physically that might make a little bit of sense. We've got a 10 kilogram mass, you know, so we're talking about 100 newtons that's out only 4 centimeters, right? So A2 is pretty small, so it's 4 centimeters. And it is, you know, a somewhat lengthy shaft, but it has a pretty hefty diameter. So, I mean, it's not that hefty, but it's 1 centimeter in diameter. So this kind of physically makes sense, especially if we're thinking that this rod is probably something like steel. Well, anyway, I hope you have found this example helpful. And yeah, thank you for watching.